Hi, everybody. Welcome back. So today we're going to talk about matching methods, specific matching methods that you can use in your research. If you haven't seen the previous set of slides on model dependence, I suggest you go look at that and then come have a look at this. The motivation, how it works, what the purpose of matching methods are, and what they do. I think they're in the previous slides. But this one says how to do it. We're going to first talk about three matching methods, how they're used in practice. We're going to zero in a bit on propensity score matching, which is the most commonly used method, but really should not be used. We're going to talk about coarsened exact matching, which is a very commonly used method now. It is also a very simple method, and it is extremely powerful. So you ought to be able to use it in your research without much trouble, and you'll understand the substantive assumptions. That's the key aspect of it. And then we'll also talk about a more advanced method called the matching frontier that we'll describe. Okay, so let's get started. So if we're going to talk about matching as a method of pruning observations so that we can find a beautiful experiment hidden inside an observational data set, we better understand exactly what type of experiment we're looking for. Now, a few lectures ago, we did talk about all the different types of experiments and observational studies and other types of research designs. So go back and have a look at that if you missed it. But today, we're going to zoom in and focus just on two specific types of experiments that have particular implications for the types of matching methods we're going to choose. So finding hidden randomized experiments inside observational data sets. When we do this, there's these two types of experiments, complete randomization versus full blocking. So in complete randomization, what we do is we have a bunch of units or countries or people. Let's imagine they're people. We flip one coin for each person, and if it's heads, we give that person the medicine, the treatment, and if it's tails, we give that person control, the placebo. That's the idealized version of it anyway. So complete randomization is the classical experiment. That's the first version of an experiment that was run. A fully blocked experiment is different. What we do with a fully blocked experiment is we don't leave everything to chance, right? Because complete randomization ensures the balance between the treatment and control groups solely by the flip of the coin. That's a great thing. That's an incredible innovation. But a fully blocked experiment can go beyond that. What a blocked experiment does is it has several known explanatory variables. It ensures exact balance on those variables first and then randomizes afterwards. And so, for example, we would block on gender by selecting two women, flipping one coin, and deciding one coin for the two women rather than two coins, one for each of the women. So we flip one coin, and heads, this woman gets treatment and this woman gets control, and tails, this woman gets treatment and this woman gets control. If you do it that way, then you guarantee that women, and then when we do it for men, are exactly balanced between the treatment and control group. Not on average, not sometimes, but in this experiment, the one that you get to run. So you don't have to think about on average across experiments. You get to look at and know for sure that you're going to have balance in your experiment. So that's a fully blocked experiment. We can think about both by focusing on the balance, and because that's really the point of these types of randomization and types of experiments. So there's balance on the observed variables, and there's a balance on the unobserved variables. For complete randomization, we get both on average. We get balance with respect to the variables we think to measure and the variables we didn't measure, and the variables we didn't even imagine that we should have measured. That's an incredible innovation. A fully blocked experiment, however, is better. You get exact balance on the observed variables, and you still get balance on average with respect to the variables that you didn't or couldn't measure. So that means that a fully blocked experiment dominates, a mathematical term, complete randomization. It is better than with respect to basically everything. It dominates complete randomization for imbalance because you're going to get less imbalance in any one run of the experiment in any one data set, the one data set that you have. You're going to have lower model dependence because there's less imbalance. And since there's less model dependence, there's less researcher discretion. There's also more statistical power because there's less random noise in your data. There's more efficiency, so you have lower standard errors and smaller confidence intervals. There's less bias due to researcher discretion. There's fewer research costs, and there's more robustness. So what do I mean by robustness? To talk about robustness, I'm going to focus on a study that I ran in Mexico for the Mexican government. What we did is we evaluated roughly the equivalent of Obamacare, except for Mexico, we were delivering healthcare and evaluating the new healthcare program for 50 million Mexicans that had basically never received healthcare before. We were rolling out, the Mexican government was rolling out this enormous program, and we convinced them that, or they were interested in, we convinced them that we would do the evaluation. They were convinced that there should be an evaluation, which is really great. The way that we did it was, since the entire program wasn't going to be offered to the entire country all at once, and we were going to roll it out to different communities, why not learn along the way? So we actually did a randomization where we chose communities and we randomly assigned building hospitals and bringing doctors and medicines and money to pay for it all, and advertising and everything. It was an enormous experiment, the largest public health or health policy experiment in history. I think it's still the largest and one of the largest public policy experiments ever. So I was running this experiment, and it was okay for me for the policy to be evaluated badly. That's okay. That might have been the consequence of the study, but it was not okay for me for the evaluation to fail. And I went and looked at large-scale public policy evaluations, and actually most of them fail. Most large-scale public policy evaluations attempt to run an experiment, or when they attempt to run the experiment, the randomization fails. Why? Because the politicians come in and they say, you know, you're in the treatment group, I think you should be in the control group, or you're in the control group, I think you should be in the treatment group. In a previous study in Mexico, some of the governors of states in the control group, it was an anti-poverty program and an evaluation of that program. The governors came in and they miraculously found enough money for the people in the control group to also receive the anti-poverty program. What a great thing from a democratic governance point of view, but what a lousy thing from the perspective of the science that we were going to learn. So I wanted to make sure that we were not going to blow the evaluation. We were going to spend quite a lot of money on the evaluation itself, and so we wanted to make sure we got it right. So robustness, not to statistical assumptions, but robustness to politics is what I focused on. And it turns out that a fully blocked experiment can do that. Okay, so let's think about a special case of a fully blocked experiment, which is a matched pair experiment. Matched pair experiment is sort of the closest blocking you can get. So we have one person who receives treatment and has a list of, let's say, 20 values of explanatory variables. Or in the case of our study of Mexico, we had one community that was going to receive treatment or might receive treatment. Actually, it was one community with 20 characteristics. And then we wanted to find another community with the same characteristics, or at least close. You could never find a community with exactly the same characteristics, but you could find one that was close. So then you take those two, and you flip one coin, and either this community gets treatment and this control, or this treatment and this control. And so we ran that experiment rather than a completely randomized experiment. Why? Here's why. In a completely randomized experiment, you flip one coin for each community. Now, suppose the politicians come in and mess up one community. Well, we no longer have a randomized experiment. Why? Because one of the observations was not the data generation process of the treatment variable was not generated by randomness. It was generated by intention. Now you might say it was just one observation, really, like you can't expect that to have a big effect. Yes, but what you're doing when you say that is you're making an assumption. And the whole advantage of randomization is you don't need to make modeling assumptions at all, right? It's just correct. if you get it exactly right. But with one observation messed up by the politicians or by however, with one observation, the difference between the treatment and control group depends upon assumption. Well, if it's going to depend upon assumption, we could just do it observationally. Well, this is better than observationally if there's only one, but of course there could be more than one. So you want to avoid the situation in which you have to rely upon assumption. Can we do that? A matched pair experiment, let's go back to the matched pair experiment, actually does that. So if you take pairs of communities that are matched as close as possible on all the characteristics we could measure about those communities, like the prior mortality rates, the current public health infrastructure, how healthy the communities are, how disparate they are, how good the road system is, the economic conditions of the community, et cetera, et cetera, et cetera. We match them in pairs, and we flip one coin and decide which of the two communities receives treatment. The other is not going to receive the health program for 3 or 4 years. The one that gets the health program, we're going to bring in all the money to build hospitals, bring in doctors and medicines and money to pay for it all. So it was consequential who gets the treatment and who gets the control, but we did it in pairs. So what happens if the politicians come in and they say, you know, Gaddy, that community you were going to be put in control? Nah, let's give them the treatment. Well, what happens then? So then what we do is we take just those two observations, and we take them out of the study, because all the rest are still randomized. In fact, there's still a blocked randomized experiment. We may change the quantity of interest, of course, because we're only inferring to the units, or really the pairs of units that we have run the randomized experiment. But the randomized experiment depends solely upon the randomization and not upon our assumptions. So a fully blocked experiment is also more robust. Okay, so all of these characteristics that we that exist for matched pair experiments. It turns out that in the literature on in public health, they thought it wasn't true for some reason, and so we had to actually go and prove it. So although we wrote a whole article that pre-registered this study that explained what we were going to do, and it was the title of it was a politically robust research design with application to the Mexican Seguro Popular or popular health insurance study. We had to go back and write another article about proving the statistical properties. Anyway, you could have a look at that. It's with Kosuke in this department, and Clayton Knoll, who is a former student also. He is now a professor at Stanford, just about to move to UC Santa Barbara, quite an incredibly beautiful place. And so we wrote this paper in statistical science and showed that all of these properties are true. And then also, we, of course, when I ran the experiment in Mexico, we could estimate the size of the standard errors, right? Because that was the whole point of it, right? But in addition, what Kosuke and Clayton and I figured out was how big the standard errors would have been if we had run complete randomization. And so then we could compare the two. And what we showed was our standard errors were as much as 6 times smaller than just because we chose complete randomization. So just because we chose matched pair experiment. So if you are running an experiment, you absolutely want to block. You get to run the experiment either for a lot less money, or you get a lot more certainty, or you don't have to run the experiment for as long. Okay, so now let's go back to matching, because the whole point of this particular talk was to find an experiment hidden within an observational study, a beautiful experiment hidden within an observational study. Which experiment would we prefer to find inside an observational study? Well, a blocked experiment, a fully blocked experiment, rather than complete randomization. We will, of course, take what we can get, but we might as well look out for where the gems are. Okay, so the goal of each of the matching methods in observational data are the following. First, there's propensity score matching, which I'm going to describe to you. You may have never heard of it, that's okay. The goal of propensity score matching is complete randomization. That's its goal. The goal of most other methods is a fully blocked experiment. So I think you know that other matching methods now would dominate PSM if when you use the other methods, they could find the better experiment hidden within the observational study. But actually, it gets worse for propensity score matching, and we're going to describe why. Propensity score matching is the most commonly used statistical matching method, and that probably should change. And so we will talk about that. All right, so now I'm going to go through 3 different methods. I'm going to give you a feel for what they look like mathematically and a feel for what they look like graphically, and then we will evaluate them. Although we'll get a good feel for what's going on as we do this. Okay, first method is Mahalanobis distance matching. The Mahalanobis distance matching method approximates a fully blocked experiment. It's looking to prune observations so that the observations left represent a fully blocked experiment. Here's the statistical procedure. First you do matching, then you do estimation. Each of the methods are going to be like this. They're going to have a different procedure for what matching is going to look like. This is a product placement, by the way. I'm not sure why no one laughs when I give these talks to myself, by myself, or to my computer. Anyway, matching. So there's the distance that we have to understand in matching, because the key part of these different methods, the way most of the methods differ, is that you have a vector of however many explanatory variables, the values of those explanatory variables for one unit, and then you have the distance from those to another. If you could exactly match, if you could find one community that was the same as the other community on 20 or 25 characteristics, then you're done. But you just rarely can exactly match because of the curse of dimensionality. And since we can't fix the curse of dimensionality, what we do is we deal with it. And the way to deal with it is some distance metric. So how do you measure the distance between this vector of numbers and this vector of numbers? One way is the Mahalanobis distance. Okay, so what is the Mahalanobis distance? It's this. It's just like the Euclidean distance, except you standardize all the variables. That's what the S thing is. So x sub c, let's do it this way. X sub c is a vector for a control unit, and x sub t is a vector for the treated unit. And we're going to look at the distance between those two points, those two observations, and it's basically the Euclidean distance after you standardize them. Okay, we will match each treated unit to the nearest control unit, where nearest is defined by this particular distance metric. In the simplest version that we're going to use right here, the control units are not reused. They're pruned if they're unused. So whichever ones lose the game of musical chairs get pruned away. In addition, we prune additional matches if the distance from the treated unit to the nearest control is too far. So we arbitrarily define a distance as a caliper, some threshold distance as a caliper, and if the closest control unit is farther than the caliper, we just say matching's not really going to do anything. We're not really going to be able to make an inference here. That observation is just too far to really do much. There are many adjustments available to this basic method. You can reuse the units. You can have multiple matches for each treatment. There's many refinements. Those refinements do often matter, but they do not matter for the points that we're making here today. Okay, so you basically match by looking for the distance, where the distance is measured in this particular way, and then you do estimation. Let's just interpret this before I show you a graph. Do you understand the distance trade-offs, first of all? So that's really important to understand, because the distance here is the center of this method. This is the way this thing works. So the trade-offs mean if you have 5 values, or let's say there's 2 values. So there's 2 values of the x's, and one is close and the other is far. Well, that's meaningful, right? Like you could, if income and education, if income is $2,000 apart for the 2 units, and education is is 10 years apart for the two units. How do you put those two together? That's what this distance metric is trying to do. It's trying to combine apples and oranges in a certain sense, right? And it's not entirely clear the right way to, I mean, it's not at all clear the right way of combining those two things. The way this thing does it is it standardizes each one and does it based upon the distance metric, right? So it does it based upon number of standard deviation units. So whether this community is close to this community depends upon all the other communities, because you first have to calculate the distance metric. You first have to calculate the standard deviation to redefine these variables. That worries me, because the standard deviation is a function of the data that happens to be in your data set, which, remember, to begin with was arbitrary, right? It's an observational data set. It's a convenience sample that you happen to get. So I'm not so sure that that's the right thing to do. Does the standardization help, or does it obscure the substance? You know, why is it here? So my generalization about this is Mahalanobis is for methodologists. In applications, we should use the Euclidean distance. So first of all, what is the Euclidean distance? It's the same thing as the Mahalanobis distance without standardizing. Euclidean distance may not be the correct thing either, because a $2,000 difference may mean something completely different than a 10-year difference, because 2,000 is a bigger number than 10. But you can scale it, right? You can make a substantive choice about how much one year of education translates into dollars. Now, you might say, I don't know how to do that, and that would be a reasonable conclusion. But if you don't know how to do that, why in the world would you expect some standard deviation of a convenience data set to do that? No way, it's not going to do it automatically. So what tends to happen is when you're writing for methods, when statisticians write things, they love Mahalanobis. They love to standardize, because what they're really trying to do is take the substance and not have to focus on the substance, so they can focus on the statistics, on the methods. They're trying to make their methods invariant to the substance. They're trying to make their methods invariant to us, which is really crazy, right? I mean, we don't want our methods to be invariant to the substance. So yes, you should be uncomfortable if you apply this method, because you have this difficult choice to make about how the distance from one variable translates into the distance from another, because at the end of the day, we have to decide whether one vector and another vector for two units are close or far apart. And that's not an easy thing. So you'll have to figure that out. Okay, so that's Mahalanobis distance matching. So what we're going to do now is exactly the same thing, but we're going to do it graphically. Again, Mahalanobis distance matching. But now we have what's going to be a graph. On the horizontal axis, we have education, one of the covariates, one of the variables we're going to control for, and age, another one of the variables we're going to control for. No dependent variable here at all. So Mahalanobis distance matching. We have some treated units, and we have some control units. So the T's and the C's, like in the graph I did last time, are basically the treatment variable for ones and zeros. Now we're going to figure out the distance. So for every unit, we find the closest, for every treated unit, we find the closest control unit. Now there's a couple of things here that we're going to ignore, because even though they matter, they don't matter a lot, and they don't matter for the argument we're going to make today, but it's worth paying attention to. So for this treated unit, we can look and see that this control unit is a little closer than this control unit, and that's why they're matched. For this treated unit, we match here. For this one, this one matches here. This one matches all the way over here. Why does this treatment unit match over here when it could match over here? Well, the reason why is because something else matched already. It is like musical chairs. And the order in which they match actually matters. So that's called greedy matching, where the order in which your data are set up actually determines the match, which seems a little crazy, right? Because it seems like you could optimize. And it turns out you can optimize, right? You can come up with one set of matches and then do another set of matches and then choose the set of matches in all the orders that turn out best. It's not a big difference, but that's one of the areas of research in matching. In any event, we now have the closest match for each treated unit. Again, that doesn't matter for the argument today. What about those C's? Well, they lose the game of musical chairs. They get pruned away. That's the data set. When you analyze the data set, you get rid of the particular matches, and then that's the data set, and you now have something closer to a randomized experiment, a blocked randomized experiment, actually. So that's your analysis. Now let's do the same thing again, a third time, but this time with a really great data set. So now, again, education horizontally, age vertically, each of those is a covariate. What we're interested in here is the treated units and finding a close control unit. But since this is such a beautiful data set, there's tons and tons of control units, and right near or essentially on top of each treated unit is a C. Every blue T has every red T has a blue C essentially on top of it, and so everything else gets pruned away. That's your data set. This is such a wonderful data set. Why? Because no matter what you do with age and education, it couldn't predict the difference between treated and control. So your control variables, your confounders are not confounders, right? They can't cause bias. So there's nothing to model. You don't need to model the difference, and you can look at the causal effect on the outcome variable, not represented in this graph, by just taking the difference in means. You don't need to control for age and education. So this is the best case. Mahalanobis does very well in this best case. It picks up and finds exactly where the closest treated units are. Not hard to find. The Mahalanobis distance is essentially 0. Okay. Let's go to the next example. The next method is coarsened exact matching. This is the method that Stefano Iacus and Beppe Puro and I came up with. It also approximates a fully blocked experiment, just like Mahalanobis distance matching. I think you'll find it a little simpler and more intuitive, and it turns out to be more powerful. So, but Mahalanobis is still a good method. You just have to get used to the distance metric. Okay, so here's the procedure. We're going to pre-process with matching, and you're going to do estimation with difference in means or model. Same exact story as with Mahalanobis. But of course, the method of matching is different. So how does it work? First of all, you temporarily coarsen each one of your explanatory variables as much as you're willing. So what does coarsening mean? So if you have years of education, you break it up into grade school, high school, college, graduate school. Those coarsened bins are your choice, right? We often break it up into grade school, high school, et cetera, and so I picked that one as an example. We then, this, by the way, it's very common. We do this kind of thing all the time when we analyze data, so I think it's familiar. In any event, we then apply the method of exact matching to the coarsened X. So you sort observations into each strata, with unique values of the coarsened X. So in other words, for every treated unit, you look for a control unit that has exactly the same values of the coarsened X. The years of education may differ, but both people will have a college degree or a high school degree or whatever it is. But you do it not only with one variable, you do it with all the variables together. You then prune any stratum, any one of those stratum defined by all the explanatory variables, the cross product of all the variables, that doesn't have at least one treated and one control unit in it. And then when you're done, you've deleted you've pruned out some observations. You take the remaining observations and you pass them on to the analysis stage. But you don't keep the coarsening. You keep the individual uncoarsened original data that you can use if you choose to model, but the model won't matter as much. There's one more step with coarsened exact matching. There's a weight that you have to use in the analysis stage. You just include it in your analysis. You do whatever analysis you were going to run previously, but you put a little weight in there. You can do it another way without the weight, and I can show you that separately. But we'll get a feel for it. The interpretation is, do you understand the distance trade-offs here? I think so. I think it's easier to understand the distance trade-offs because we're just using the method of exact matching within the coarsened bins. right? So for the coarsened variables, these 20 variables have to match some other variable within the coarsened bins. If they don't match, if you don't have enough observations, then you can, if you choose to make that substantive choice, you can increase the size of the bins, right? You can say college, no college, right? Instead of high school, college, graduate school, etc. So that's your choice. That's a substantive choice. And I think you understand that if you use more coarsening, matching is not doing as much. You might leave more model dependence on the table. But if you use more coarsening, you'll end up with more observations. So it's a trade-off that you'll have to resolve. But all the decisions, to me anyway, are utterly substantive. I think you can justify or not justify or make a decision about any particular coarsening, and that's the key. Like I just want to make sure that when we make assumptions, that they're connected to the substance, so we can make a substantive argument. That's where we're on our strongest grounds, not appealing to some kind of statistical thing that nobody's really paying attention to, like standardization, but to the substance, because those assumptions then depend upon all the prior research in the field. And if there is some prior research, we can depend upon it. Of course, if there isn't, then we're guessing in either way. What do you do if you have too few observations? Just like I said, you increase the bins, right? But if you increase the bins, you end up with potentially more model dependence. So you have to deal with that. Okay, let's look at the same thing, but graphically. So again, education horizontally, age vertically, both of them are pre-treatment covariates that we're going to want to look for, that we're going to want to control for, and use matching to reduce the effect of for when we get to modeling. So again, we have a bunch of treated units and we have a bunch of control units. Now we have to coarsen these. So I will use the humor of my co-author Rich Nielsen, and on the vertical axis we have the official category of old, retirements, senior discounts, etc., drinking age, etc. That's not that funny, but on the horizontal axis we have high school, BA. My favorite part here is my hard driving graduate students, right? They see the horizontal axis and they say, you may say, high school, BA, MA, PhD, second PhD, what are you talking about? Anyway, this is a joke. You'll have to justify these things substantively. So instead of years of education, we would use these choices or some other choice, and similarly for age. Now I'm going to draw a line for each one of these thresholds, and now together we have a bin. Of course, these bins are in 2 dimensions. They can work for any number of dimensions. But now notice that for some of the bins we only have control units. Some of the bins we have treated and control units. The distance metric here is 0 or 1. Either you're in the same bin and you're close, or you're not in the same bin and you're infinitely far apart. That's the idea here. And so these guys go away. See that? They all go away because they don't have a partner in their bin. So we drop them. Then I'm going to go one more step, and I'm going to try to visually convey to you what the weighting is. So if you just have a look here, there's only 1 treated unit, and there's 5 controls in this particular bin. So that's fine. But you could do it without weighting, but within that bin, if you wanted to estimate a causal effect, you'd average the C's and subtract it from the T. Right? So you can do that. You can average the C's and subtract it from the T, or you can just apply the weighting to the entire data set, all like that, and then you don't have to think about the averaging within each one. So that's what the weighting does for you. Okay, let's do the best case, of course, in exact matching. What's the best case? The best case is you choose not to use any coarsening at all, or you use very, very fine-grained, I'm sorry, it's not any coarsening, it's very, very fine-grained coarsening. But with this wonderful data set, with each T near or essentially on top of each C, then there's a great match there. And since the coarsening is very, very fine, we can still find it, right? And then that's what the data set looks like. Right, and this is again a great data set because education and age can't predict whether you're treated or control, right? Because treated and control, each one of them are very, very close to each other. You can't distinguish them. Okay, so that's the data set. That's what would be passed on. let's do our third method. The third method is the most commonly used method that you'll see out there. It's called propensity score matching. It approximates a completely randomized experiment, not a fully blocked experiment like CEM and Mahalanobis. Here's the procedure. Like the other two, you pre-process your data with matching, and then when you're done pre-processing, you do estimation with the difference in means or a model. But the matching works differently. So here's the idea. So first, you reduce the k elements of x to a scalar, to one number. How do you do that? You run a little logit equation, where it's not the main logit because there's no dependent variable involved. But you take t, the treatment variable, and you make that temporarily your dependent variable. And you regress that, you run a logistic regression of t on all your pre-treatment confounders. And this thing, the probability of t equaling 1, right? It's the logit, this is the logit function, 1 over 1 plus e to the minus x beta. That's the same logit functional form. We know how to estimate beta. We just use the same procedure we've used before. But this thing, which we're going to call pi, is what's called the propensity score. And the way you would interpret it is it's the propensity to be treated. It's the probability of t equaling 1. Okay. Now, what do we do with that? So we define a distance according to propensity score matching, or PSM, where the distance is just the distance between those two pi's. Pi for the control group and the nearest, and the pi for the treated group. That's the distance. It's not in k-dimensional space. It's only just in that one-dimensional space. Then, just like with Mahalanobis, we match each treated unit to the nearest control unit. In the simple version, the control units are not reused. We prune them if they're unused. And similarly, like Mahalanobis, if one of the matches is too far defined by the pi's, right? So if the pi's are too far from each other, if a treated pi is too far to the nearest control unit, then you discard the treated units as well. There's, again, many adjustments available to this basic model. They do matter. They don't matter for the arguments that I'm going to give you today. Okay. How do we interpret this? Do you understand the distance trade-off? Same question, of course, for all three methods. Think to yourself, do you understand whether an observation is farther from another observation? Well, one interpretation is the distance there is the probability of treatment. One would have maybe probability of treatment of 0.7, and the other would have probability of treatment of 0.8, and they differ by 0.1. So substantively, what does that mean? It's not entirely clear. It's pretty hard to get a completely good feel for it. The intuitive part of it is that that logit, the coefficients in that logit, are picking up the variables that distinguish between treatment and control. So if the treatment is completely unrelated to the x's, like in the best case of the previous methods, then those coefficients, right, they shouldn't actually predict the differences. But wait, we'll see. So do you understand the trade-offs not only statistically but substantively? So remember that case where we had two explanatory variables. We have a $2,000 difference in income and a 10-year difference in education. What does this say about that? Well, it's not entirely clear because it depends upon how much of an effect each of those has on the treatment, and it's all sort of mushed up together. So it's a little difficult to figure out exactly what's going on, but it does seem to simplify things, and the intuition is, well, I'm never going to be able to find matches in k-dimensional space, but maybe I could find a match in one-dimensional space. Well, the theory here is that the matches are exact, and it turns out it's not actually easier in one-dimensional space to find an exact match because there's an infinity of values than it is in k-dimensional space. So that's not entirely clear either. So what do you do when one variable is very important? That is, has a big effect on the outcome. When one variable has a big effect on the outcome, that is on y, then you want to make sure to control for that variable well. You want to match on that variable well. Is that in the propensity score regression? Well, it can't be in the propensity score regression because y is not in the regression. So the importance of the variables is not there. You would know the importance of these variables. If you're in political science, you know that party ID matters, the lag vote matters. If you're in public health, you know perfectly well that age and education and prior health status matters, right? In every field there's some of these, but how do you get those into the propensity score? It's not entirely clear. Okay. Let's have a look at propensity score graphically. Again, I have age horizontally, age vertically, education horizontally with some treated and control units. How do we figure out the distance? First, we take all those points and we create a propensity score, which goes from 0 to 1. That's the pi, probability of a treatment. We take each of those things and we project it out to this one-dimensional space. I'm showing you 2 dimensions here because it's easy to show you 2 dimensions. Of course, it could be 20 dimensions. It's still getting projected down to 1 dimension. Then you temporarily throw away the data and you do the matching on this 1 dimension. So this treated unit is matched to this control, and this treated unit is matched to this control. That's the idea. And the ones that don't match, they lose the game of musical chairs, and they go away. Then you take the data. Then you take these, you project them back into the space, and that's the subset of the data that goes on to the analysis stage, right? That's the idea of these data. Let's look at the best case. So the best case of propensity. Actually, let me just go back here. So do you have the feel for the fact that maybe we're losing some information because we're matching on 1 dimension, even though the data exists in k dimensions? That's the feeling I want you to have. I think you're going to see the feeling when we get to the best case, which is right now. Okay, best case, propensity score matching. So again, we have this wonderful data set. Every treated unit is essentially right on top of a control unit. And so the matches are really there. You could really find them. You just need a method to find them. So let's project these to the propensity score. But let's pick a really good case for the propensity score. Let's suppose they're all the same. Now you'd say, wait a second, when could all the propensity scores be the same? Actually, if you're running a randomized experiment and you're flipping coins, the propensity score, the probability of receiving treatment, they're all 1s, right? So I'm sorry, not 1s. The propensity scores are all 0.5s, right? Because the probability of a heads is 0.5. In this case, the probability of a heads is 0.2, right? Because they're all down here at the bottom. But nevertheless, that's fine. They're all the same. That means it's easy to match them, right? Okay, so we go there. When we match them, what did we get? Wait, let's start there. Remember, it's a beautiful data set. We go here. Now we match. Now wait a minute. How do we match? Everything matches. Every unit matches to every other unit, right? Because they all have the same propensity score. So wait a second. So every treated unit matches to all the controls. So if we do 1-to-1 matching for every treated unit, we find 1 control. Then how do we choose among the controls? That's a clue. Propensity score matching chooses among the controls, in this case, randomly. It's randomly choosing observations to put into the to prune. And so how could matching improve here? What you wind up with is this data set. This data set is not an exactly matched data set. This T is not on top of the C. It's farther from it. I mean, it's not bad overall, right? Overall, the distribution of the T's and the distribution of the C's are about the same, right? And that makes sense because propensity score matching is shooting for complete randomization. If you're flipping coins, then on average, the distributions will be the same. But although the distributions of age and education are the same, the actual values in the experiment that you ran, the one experiment that you ran, is different. That's a bummer. Okay, so propensity score matching is clearly suboptimal. Even in the best case, it doesn't get it exactly right. Okay, let's just go into propensity score matching in a little more depth because you're going to run into it out there in the real world because propensity score matching is so common. I want to explain the problems, but first, let me give you a fact. And this fact was a real surprise to me. I've even said the opposite in print, and it was a surprise to the literature. But you need this fact in order to understand what propensity score is doing. And the fact is, random pruning, which remember in that case that I just showed you, propensity score matching does, increases imbalance. Now that sounds crazy, right? So you have a treated group and a control group. If you randomly delete observations, they should still be the same distance apart, right? Wrong. That's not true. Okay. So deleting data only helps if you're really careful. So let's think about this. Actually, think about it this way. Suppose we were actually in a classroom, right? Remember back when they had those things? We were in a classroom, and I would say, think of how close you are to the nearest person. Okay, now let's randomly delete half the people. Well, let's rephrase that. How about half the people are asked to leave? Okay, now ask yourself the same question. How close are you to the nearest person? You're actually farther away, right? So that's the first hint that random pruning actually increases imbalance. But let's look at it more precisely. Random pruning is by definition a process that is independent of X. So here's a very simple example which is discrete. It's the simplest possible case. Remember, following that rule of methods in order to really understand methodology, what you want in a particular case, for if you have a particular question, is look for the simplest possible case. So here's what I think is the simplest possible case. We have a sex-balanced data set. So we have two treateds and two controls. We have a male and a female and a male and a female. Okay. Now from that, I'm going to randomly prune two observations, one from each data set. So I'm going to be left with this, with a data set with only two observations drawn from the observation with four. Now ask yourself, how many different data sets could be drawn from a data set of two if we do it that way? Well, there's four. So I'm going to randomly prune one treated and one control. There's four possible data sets. There's two that are balanced and two that are imbalanced. That is, if there's male and female, then you could delete the two. Maybe I shouldn't use those fingers. Okay, anyway, there's two males, and you could wind up with two males and two females, or you could wind up with a male and a female and a female and a male. So there's two balanced and two imbalanced. So in other words, when you're randomly pruning from a data set with four observations, half the time you wind up with data sets that are perfectly balanced, a male and a male, female and a female, and half the time you end up with data sets that are imbalanced, a male and a female and a female and a male. Right. So what does that mean? That means random pruning increases imbalance. Okay. It works in the continuous case as well. If you have a data set, let's say t, which is the treatment variable, randomly assigned by flips of coins, let's say, and x is any fixed variable with n units. Here's a measure of imbalance: the squared difference in means. Right. So you have the difference in means. Just square it. Right. We could take the absolute value, but let's just square it. Turns out the expected value of our distance metric, the squared difference, is the variance. Okay, so the variance is proportional to n. Proportional to 1 over n. And random pruning. So if you do random pruning, then n declines, because when you prune, you decrease n. If you decrease n, the variance increases, and therefore the expected value of our distance metric increases, right? So random pruning, again, increases imbalance. This result turns out to be very general. It doesn't only apply to these two cases. Okay, so moral of the story of this slide, you prune randomly, you increase imbalance. PSM, propensity score matching statistical properties. It has low standards. Sometimes it helps, it never optimizes. It's efficient relative to complete randomization, but it's inefficient relative to the more powerful fully blocking. Other methods dominate it, and here's the interesting way to think about it. If you have exact matching between XT and XC, then you get exact matching on the propensity scores, no question. But if you have exact matching on the propensity scores, which is the goal of the procedure, you don't get exact matching on the X's. I showed you that in the best case graph, right? So that's really weird. And the real thing is the literature, the applied literature, the methodologists totally understand the method. The applied literature shows that, or the applied literature is written as if this second line had an equality, and they don't care about the first line. They think that you take the data and you can't match in 24 dimensions, you reduce to 1 dimension, and that's all you need because there's this great propensity score matching theorem. But the propensity score matching theorem doesn't say that these two things are the same. They're not the same. Okay. The propensity score paradox. Now I'm going to give you one more thing. Okay. When you do better, you do worse. So here's the idea. Random matching, as we now understand, increases imbalance. When PSM approximates randomization to begin with or after pruning, what's it doing? Well, at that point, it's increasing imbalance. At that point, it's pruning randomly. Now, wait a second. Let me say this again. For starters, propensity score matching, if you start pruning observations, it's pruning the right observations. It's improving imbalance. It's reducing imbalance. But at some point, you get to the point of complete randomization when other methods would keep going from after they found the complete randomization experiment, they'd go for the fully blocked experiment. What propensity score matching does is it actually makes things worse, because it's pruning at random. When it's pruning at random, basically, when propensity score matching approximates complete randomization, all the pi's are roughly the same or constant within their strata. That is pruning at random by definition. I showed you that in the graph. That produces imbalance. It generates imbalance. So you have a procedure that is designed to reduce imbalance, and it increases imbalance. Of course, imbalance produces inefficiency. Inefficiency produces model dependence. Model dependence produces researcher discretion. Researcher discretion then generates bias. So that's a bummer. If the data have no good matches, so there's no good matches in the data at all, won't propensity score work? Well, the paradox won't be a problem, but you're cooked anyway, because if the data have no good matches, there's no method that's going to make them good. All right. So a lot of people ask when I give this talk, doesn't propensity score matching solve the cursor dimensionality problem? No. The cursor dimensionality problem is not a problem to be solved. Like, that's sort of like solving the problem of gravity. Gravity is not going to be solved. Gravity exists, at least so far as we know. The propensity score paradox, in fact, gets worse when there's more covariates. It's more of a problem with more covariates. The pruning causes an increase in imbalance faster when there's more covariates. Okay. Let's have a look at this graphically so we can have a real good feel for this. So here, I made a data set. And the data set has two explanatory variables, x1 and x2. And I put in the data set, for starters, a completely matched pair experiment where each t is essentially on top of each c. So this is a wonderful experiment. I then made a completely randomized experiment and threw them in here as well. The distribution of the t's here and the distribution of the c's here look the same, but the exact matches don't exist. So they're not pair matched in this data set. It's just the distributions look the same. This is a wonderful data set. This is a pretty good data set. And then what I did is I made it a messy observational data set by throwing in a bunch of control units that are not particularly close to any of the treated units. So together, the whole data set is a big messy observational data set. Now let's suppose that what we want to do is use matching to analyze this data set. If we use the entire data set, then we throw it into a regression, we're going to have to use these to try to figure out where the t's are that have similar values of the explanatory variables. So we're going to have to extrapolate very far. And that extrapolation is not going to be a good situation, right? We're going to have much more model dependence. So if you want to get rid of the model dependence, what you could do is look inside this data set and see if we can identify a wonderful experiment. Right, and hidden in here, and we can. All we have to do is get rid of the C's. You know, we might want to get rid of these, and we would be left with this. We could, of course, also include this, but basically, this is. If we found this, we'd be thrilled. If we found this, we'd be happy, but not thrilled. And if we don't do anything, we're going to have a lot of model dependence. All right. So now, we take that data set. This of course was randomly generated by me according to those by us according to those rules. We randomly generated 1,000 data sets just to make sure that it wasn't this one data set that was causing the issues. So now I'm going to explain these graphs on the right. On the right, each row of pixels here is a different iteration. They all look roughly the same. First, I'm going to start with Mahalanobis. What we do here is for the first row of pixels, which refers to this data set, is I start off with the whole data set. And I look through this data set according to Mahalanobis distance matching, and I look for the first observation to drop. Which one do I drop? I drop the worst match, maybe one of these, because it's the farthest from any control unit to any treated unit. So maybe something along this ledge. And it's black, it's color-coded here, right? So you can see that, right? So we drop the worst match. Then we drop the next worst match. Then we drop the next worst match. Then we drop the next worst match. All the way from the left here to the right, right? Because the horizontal axis here is number of dropped observations. So we go from the left to the right, from worst observation, the worst match, all the way to the right. And you see what Mahalanobis does. It identifies the worst observations, these control units that I threw in just to mess things up. Then it finds the pretty good experiment and deletes those. And then if we force it to delete more observations, it deletes some of these. So Mahalanobis is doing exactly what we would want it to do. What does propensity score matching do? Propensity score matching absolutely finds these C's. It finds them exactly as it should. It deletes them first. And then it can't see the difference. It's blind where other methods can see. It can't see the difference between a perfect, wonderful experiment and a pretty good experiment. It can't see the difference. And so it's basically blindly choosing between these two. So you see that? This is a real cool graph. I really like it. I hope you do too. Here's another way to think about this. So what does propensity score matching actually match? So let's have a look at this. Well, again, we'll compare MDM, Mahalanobis distance matching, and propensity score matching. Over on the left side here, there we go. Over on the left side, here's what I did. So x1 and x2 are two pre-treatment covariates, no dependent variable here. Within this square, I uniformly plotted a bunch of dots, blue dots. In this square, in this pink square, I uniformly plotted a bunch of red dots. Then that's my data set. And you can see, of course, in here is the overlap region. No necessarily exact matches, because what we did here is we designed this for propensity score. So we're not going beyond its capabilities. We're not going to a fully blocked experiment. We're just focusing on complete randomization. So we did complete randomization, but with an overlap region that we wanted to find, and with this region that has no blue dots, and with this region that has no red dots. Okay, so the treated units are supposed to be the red ones, and the control units are the blue ones, and this is where we wanted to find matches. Mahalanobis distance finds the matches in reasonable ways. What we do is draw on this graph lines between a blue dot and the nearest red dot, and we just drew them darker when they're closer and lighter when they're farther apart. So the better matches are both closer and darker. They're closer because of Mahalanobis distance. They're darker because Mahalanobis says that they're closer. So that's a good thing. They're completely consistent with one another. I'm essentially encoding the same information twice, but only with respect to Mahalanobis. So this all makes sense. In this graph, we're using the same points, not the same data generation process, but exactly the same points, right? You see, like, this point is here, this point is here, these 2 points are here, these 2 points are here. But instead of using Mahalanobis distance, we're using propensity score matching. And here you can see that propensity score matching, because it does the matches in a completely different space, because it does it on the space of the propensity score, it doesn't get what's going on here. And so it finds that this point is close to this point because there's a dark line between those 2 points, even though they're very far apart in the space of x1 and x2. Now, you might say, well, that's what it's trying to do, right? It's trying to find points that have similar propensity scores, and obviously the reason they were matched is because they have similar propensity scores, so what gives? What gives is that we're substantive. We're interested in the substance here, not in some mathematical construct. And if these 2 points are far apart on x1 and far apart on x2, they shouldn't be matched. Like, I don't really care whether they have a similar propensity score. So this is the weird thing. Okay, let's go another step. So now what we're going to do is take that data set and we're going to make a dependent variable, which we haven't had at all so far when we've been talking about propensity score. And we're going to see model dependence in action. Like, we're going to measure model dependence and see what the consequence is. All right. So what we do is we take the x1 and x2 from the previous graph and t, and we run a regression. We generate data. We generate y in the following way. And y is equal to this regression equation, where 2 is our causal effect. I just defined it as 2, times our treatment variable. The constant term is 0, plus 1 on this variable, plus 1 on, as a coefficient on this variable, 1 on x2, and then this is normal. Okay, so that's our data set. All right, next thing we did is we're going to try to measure model dependence. So we run that regression. But of course, when we have an observational data set, we don't know what the right regression is to run. So we ran lots of different regressions. We included t and x and x1, and sometimes x1 only, and sometimes x1 times x2, and sometimes x1 squared, and sometimes x2 squared, and sometimes x1 times x2 and x2 squared. We ran more than 500 regressions. Okay. Then in every regression, we estimated the causal effect. We estimated the coefficient on t. We're trying to estimate the 2. But of course, we don't know what the 2 is. What happens? For starters, what we're going to do is we're going to look at the variation, the variance, across the estimates, across the different models. Model dependence is the variation in the estimates across the different models. We want that to be small. So if we start with the original data set, it's here. The vertical axis here is the variance, the amount of model dependence. The horizontal axis is the number of units pruned. So right here at 0, we have the original data set with no matching. This is how much model dependence there is. Let's just call it high, but it's whatever that level is. We then prune the worst possible match according to Mahalanobis distance matching, and the model dependence declines. We prune the next match, model dependence declines. It declines because we rerun the 500 regressions, and we calculate the variance, and we plot it. And then we find the worst match, we prune that one, and we rerun the 500 regressions, calculate the variance, and we plot it. We do that, and for Mahalanobis distance matching, the amount of matching, the amount of variance, the amount of model dependence goes down, 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 all the way to essentially 0. Okay, so that's MDM, Mahalanobis distance matching, exactly as we would expect. What happens with propensity score matching? With propensity score matching, you go down, you go down, you go down, you go down, and then when it hits the point of complete randomization, the variance starts going up, which is completely nuts. Like why is that happening? It doesn't really make any sense. Okay, it's happening because random pruning, which is what it's doing after it gets to complete randomization, at that point it is randomly pruning and increasing imbalance. Okay, one more step. We tried to estimate 2. Here's a vertical axis. 2 is right here. The true effect is 2. On the horizontal axis, again, we have the number of units pruned. We're going to start here, and it turns out the original data set without any pruning produces an estimate of 4. We then prune according to Mahalanobis distance matching, and the average of the results, which is what we calculate, get closer and closer to 2, closer and closer and closer, until basically it hits 2, and it stays there, right, as you prune. So the pruning is basically doing its job. The variance is larger here, and it's also giving the wrong answer. The variance is much smaller here, and it's giving the right answer. What is propensity score matching doing? It's getting closer. It's doing the right thing. It's deleting the C's in the ones that are far away, and then it hits the ground, and it actually starts going up. So it's not what you want. I mean, it's like you walk into a shoe store, and normally you say, "Here's some money," and you get a new pair of shoes. But instead, what happens in the propensity score matching shoe store is you say, "Here's some money," and then they ask you for your shoes, and you give them your shoes. It doesn't make any sense. Okay. Does it happen in real data? Let's see. This is an article from the Journal of Politics by Steve Finkel and company. The vertical axis, we measure imbalance in one of our ways. The horizontal axis is number of units pruned, just like in the last graph. For calibration, we start with the raw data. which is right here. That's how much imbalance there is. The point of matching is to reduce imbalance. Let's randomly prune, actually randomly prune an average over the randomly pruned data sets. This is what happens. It's the dotted line. Of course, it increases because we know random pruning increases imbalance. Then we run Mahalanobis distance matching. I'll get the best for last. Mahalanobis distance matching starts with one-to-one matching, so it jumps to over here. And as we prune observations, imbalance drops. CEM, as we decrease the coarsening, right, imbalance drops. Exactly as you would expect. What happens with propensity score matching? Propensity score matching starts here with one-to-one propensity score matching. Then you crank up the caliper and follow the rules even better. And it basically parallels random matching. It's slightly better than random matching, but it is not something you want to do, because as you delete observations, thereby increasing inefficiency, you're also increasing bias and increasing imbalance, which is completely nuts. It also works in this other paper by my co-author, Rich Nielsen, that he wrote before we figured all this out. In fact, we had such a hard time Rich and I had a hard time figuring all this out that we thought, let's go get a whole lot of data sets. We saw this pattern that it would keep going up, and we just didn't know how to figure it out. And so we thought, we need a lot of data sets. So we advertised on the web, and we said, hey, anybody have any data set that where you're using right now, it's not published, you're trying to do matching for causal inference, send us the data. We won't publish your data. We won't scoop you. We won't tell anybody that you sent us the data. We'll use it for our research. We'll analyze the data. We'll follow best practices. We'll do the best we can, and we'll give you our results, and you can use it any way you want. And so we got more than 20 real data sets, and we saw this pattern basically in all of them. Right? At some point, it starts going up. At some point, propensity score matching makes things worse. It may start by improving things, and actually in Rich's paper here, right from the raw data down to here, it actually improves things. But then if you increase the caliper, it starts going up and up and up and up and up. So it's not the kind of thing that you'd really want to do. Okay, last topic for today, the matching frontier. There's tensions in existing matching methods, in the matching methods that I described. If you maximize on one metric, you should judge yourself on that metric. But instead, we're going to judge ourselves on a different metric. So it's sort of a little crazy. In propensity score matching, even in the original articles on propensity score matching, they say, run propensity score matching. And the first thing you do when you're done with this technique designed to reduce imbalance is go check to see whether it's reduced imbalance, which is a little crazy, right? Like if it's supposed to reduce imbalance, why don't you just measure imbalance, optimize a way to reduce imbalance? But instead what it does is it runs its propensity score thing, and it does one-to-one matching. So you wind up with the number of observations that you expect. It's optimizing with respect to that, but not with respect to imbalance. So you're basically choosing n in that way, and then you check imbalance afterwards. Mahalanobis works the same way. You choose one-to-one Mahalanobis distance matching, one-to-one for each treated unit, find the nearest control unit. And then when you're done, you end up with twice the number of treated units in your data set. That's how many observations are left. But the amount of imbalance that you wind up afterwards, you have to see. I mean, you'll know it as you're doing it because the distances are clear, but you basically have to summarize it. In propensity score, what the authors of the original papers suggest that you do is you run your propensity score matching algorithm and then compare the mean in the treated group for variable 1 to the mean in the control group for variable 1, the mean in the treatment and control groups for variable 2, for variable 3, etc. And then the variances, and then maybe some other characteristics. So there's other matching methods that work differently. Instead, what you do is you choose the imbalance you're willing to deal with, and you check the n afterwards. So exact matching works that way. You decide that I'm not willing to tolerate any imbalance. you find for every treated unit any control unit that exactly matches on all the variables, and you prune everything else. Or CEM, you find any control unit that exactly matches within the coarsened bins, and you throw away anything else. And so what happens is when you're done with that, you wind up with exactly the imbalance that you chose ahead of time. Because ahead of time, you chose the coarsened bins. That's the amount of imbalance. That's the maximum imbalance that you can possibly have. But you don't know how many observations are going to come out the other side. For exact matching, there may not be any exact matches. For CEM, you may have set the coarsening in the wrong way, and you'll wind up with no observations. So both of these sets of methods have this sort of odd part. And they have this kind of characteristic where you push down one problem and it pops up another. So if the difference in means let's go back and do this again. So all of these methods have a particular problem. And they're in two categories, right? One, you don't know what the n is at the end, and the other is you don't know what the imbalance is at the end. The propensity score methods these others, they all have this characteristic, right? So what happens is you try to achieve imbalance, and you don't have a good end. So you go back and you fix the imbalance. I'm sorry. If you try to get good imbalance, you'll get good imbalance, but then you might not have enough observations. So then you try to fix the number of observations, and you won't get good imbalance. Or in the difference in means when you're doing comparing that for the propensity score, what happens if the difference in means for x1 is big and for x2 it's small? Well, you go back, and the recommendation in the propensity score literature is go respecify the propensity score regression or put in different variables or something like that and run it again. And what happens often is you'll reduce the imbalance on x1 and increase it on x2. So it's a little like the sort of whack-a-mole kind of situation where you fix one thing and the other thing gets worse. And it's actually quite frustrating to run these methods because the point of them is to reduce imbalance for the largest number of observations possible. And it's not doing that. You sort of have to do it by hand. Okay, so here's what the matching frontier does. Horizontally, we have the number of units pruned. Vertically, we have imbalance. Number of units pruned. If you prune very little, then if you prune very little, you're going to have low variance. If you prune a lot, you're going to have high variance. Imbalance, down here, you're not going to have much bias. But up here, if there's a lot of imbalance, you're going to have a lot of bias. So there's a trade-off between these two. If you think that this is result 1 and result 2 and result 3, those are the particular matched sets that a particular method might produce. This is the matching frontier. It's the theoretically optimal frontier. And the idea is that it is impossible to get down here to lower variance, lower bias. You can't get anywhere lower than this. In other words, there doesn't exist a matched data set, a subset of your data that could do better than that. But, like you would probably want to choose result 1 and not result 2 because this is closer to the frontier. But, if this is the frontier, that means there's matched data sets that are on the frontier. So why the heck not find the frontier and find a data set that's at least on the frontier? Okay, we're not going to be in the impossible region. So how hard is it to calculate the frontier itself, like to find the frontier? Because that would be the solution, right? It would be the best possible trade-off between number of observations and imbalance. So let's consider one point on the SAT frontier, sample average treatment effect on the treated. And you start with the matrix of n control units. You calculate imbalance for all big N, choose little n subsets of rows of X, okay? Because a subset means anything else we prune. We're going to choose the subset then with the lowest imbalance, given n. How many evaluations do you need to compute the entire frontier? So you need n choose n for each sample size, n minus 1 after you prune one observation, n minus 2 after you prune the second one. Well, the combination of this is called the power set, and it's really, really big. For example, if n is greater than 300, then you require more imbalance evaluations and looking for all subsets of the big set than there are elementary particles in the universe. So it's like a lot. So it's pretty hard to calculate. So going to the frontier, like you can see why people didn't start with the frontier. They started with these methods that produced something that sort of seemed reasonable. Rich and I, in this paper, we figured out ways of calculating match data sets from the frontier. They run fast. They operate as greedy algorithms, so they're fast, but it turns out we proved that they're optimal, the particular algorithms we came up with. They don't require evaluating every subset. They work with very large data sets. It's the exact frontier. There's no approximation or estimation. It's exactly what you want, and it turns out it's easy to calculate. So I'm not going to, in this talk, show you the algorithm, but I'm explaining that the algorithm exists. It's written in software. You can go to the Matching Frontier website and you can download the software. It's easy to use if you have an appropriate data set. Just to give you a feel for it, let's construct the feasible sample average treatment effect on the treated Mahalanobis frontier. So here's what it looks like. If we have a data set like this with covariate 1 and covariate 2, each treated unit is proximate to a control unit. I'm going to show you a working version of the algorithm. It plucks out data in exactly the right order such that it would have the frontier. On the right here, I have the frontier. This is the number of observations that we're going to drop, starting with the original data set, which is right here. The vertical axis is imbalance. It's another measure of imbalance. I'm then going to delete the one observation that will reduce the frontier the most, so it can it will reduce imbalance the most without it's going to drop one observation, and when you drop one observation, it's going to reduce the imbalance the most, right? For every observation, we want to get the biggest bang for our for the observation that we prune, and so. That was the one. This one is that one. And basically, the algorithm is working on the left that I haven't really explained to you, but this traces out the frontier. And then once we have that frontier, then there's no proofs here, so be careful. This is the frontier for this particular data set. It's impossible to be down here. There's no data set that could have fewer observations dropped and lower imbalance. You could be up here, that would be dumb, but you'd want to pick something on the frontier. With this method, you can pick something straight from the frontier. There's also an algorithm for discrete points, and I'll just show you the way it works. You pluck out those points, and so it traces out the algorithm. Okay, so that's basically the way it works. Okay, it at least looks pretty. Okay, so with this, that's basically a signal that if you want to use this, you go back, you read the paper in more detail, come by, ask questions, and we can figure it out. But that's the direction in the literature, trying to figure out how to optimize imbalance and the number of observations at the same time. To give you a feel for what it looks like in practice, here's a commonly used data set. It's from Lalonde, who in 1986 published a really cool paper in economics where he worried about what we would call model dependence, and he found an experimental data set and an observational data set, and then he tried to estimate the same number that the experimental data set would produce from the estimate, just from the difference in means, from the observational data set. And he showed that, gosh, you wouldn't necessarily get back to the answer, and so you'd get all these crazy results. And so everybody reanalyzes the Lalonde data, right? Matching was introduced in widespread usage after the Lalonde paper, and so people tried matching on it, and they tried lots of different methods of matching on it. And so a good prediction of whether an article is a methods article or a substantive article, you only need one variable, which is did they use the Lalonde data or not? Anyway, so we're using the Lalonde data today. This is the frontier. the number of observations pruned. The vertical axis here is is a measure of imbalance, where you start off with this amount of imbalance, and the imbalance drops and drops and drops in this way. But it drops in a particular way. There's 16,000 observations. This data set has only 185 treated units and 16,000 control units. What this shows, however, is that you don't really get a big reduction of imbalance until after you've deleted about 15,000 observations, and then you do. Now you'd say, wait a second, you're going to prune 15,000 observations? And the answer is, wait a second, suppose you could have done a randomized experiment that would produce no model dependence, no bias, but you only had 185 treated units and let's say 185 controls. That'd be a pretty good deal, right? So you can delete, 15,000 or more observations. That's fine. You get all the way down here with very low imbalance, and there's still a good number of observations left. Another thing we did along the horizontal axis, again, is the number of observations pruned. I put that also on the horizontal axis here. And on the vertical axis, we have an estimate. This is the truth, at least according to the experiment. So in the job training program, it got people an extra nearly $2,000. If you run a regression in the observational data set, it turns out it's negative, like the job training program hurt people. This is the variance in the estimate. And then as you prune, this is what happens to the data set, right? As you prune, you get it gets better and better and better and better. And then eventually it gets close enough and it crosses the real line. So that's just a good example of, in this particular data set, it turned out to be better to prune quite a lot. In other data sets, they won't be large. You won't want to prune a lot. You can actually get to the right answer, at least in this example. And you get to see it all. So I wouldn't suggest picking one point on the frontier. Instead, I would suggest plotting the entire frontier, and then here's the causal estimates all along the way. If you want to interpret this as there was bias all along the way until we got rid of it, then we finally got to the right answer, that's fine. If you don't believe that and you say there's not, the answer here may have relatively little bias, but it's got massive inefficiency relative to having 16,000 observations. If you want to stop at that point in the bias variance trade-off, that's totally fine. Okay, so matching helps reduce model dependence. That means that you can use it as pre-processing to fix up your data a little bit, and that will take your modeling and make it a whole lot better. It will make it so the outliers aren't big leverage points. It will make it so that the decisions about whether to put squared terms or interaction terms in there won't matter as much. It will make it so that the choice of the functional form and the stochastic component don't quite matter as much. Matching isn't always possible. Sometimes the number of observations that we have to begin with is relatively small. Sometimes, as we've seen in the examples here, there are no close matches, and the only way to make an inference is with a model-dependent inference. What do we do in that case? It depends how important the result is, how important the substantive problem is. If it's a really important substantive problem, model dependence, so we deal with model dependence. That's what we have. If you want to estimate something that is really important, you're going to want an answer regardless, right? And so if you have a lot of model dependence, you just be honest about it. You have to be utterly honest about it, convey the model dependence, make your case as to why you've chosen the right model, but convey the fact that if you chose the wrong model, you get the wrong answer. And the solution then is to go out eventually and see whether you can find some more data. So matching is a tool that will get you a little closer. Sometimes it's a non-parametric method of pre-processing data to help your modeling efforts. Okay, so I'll see you next time. Thanks for listening.